Okay, good afternoon, everyone. Sorry about the delay. Let's get started and wrap up chapter 4 for us. All right, logic circuits. We stopped here where we were talking about the rising and falling edge of the clock. Okay, so any questions? Any questions so far? So that is for explanation purposes. You're talking about the arrows. The arrows are not generally indicated. It's just basically just showing that, there's a transition that is taking place from high to low, and here where it goes from low to high. So this is a falling edge because the value is falling from 1 to 0, and the other one is a rising edge because, well, it's rising from 0 to 1. But anyway, that's the reason why we use, sorry, not the reason. This is what it meant by a edge trigger, meaning the input of any flip-flop or the logic circuit is synced with the edge of the flip-flop, not the level. Okay, not the level. So the level is, of course, here for the entire time period, right? But we are working with the edge, not with the level. And so from there, we talk about a flip-flop known as the D flip-flop. The D stands for delay. And delay because it is synchronized with the clock, the rising edge of the clock. And the edge is noted by this symbol. And that symbol resembles the tip or the edge of the knife. Hence a edge. So if you see this kind of symbol, it's indicating that it is a edge trigger. Edge trigger. And oftentimes you might have the bubble would indicate negative edge triggered, which if you were taking the lab, there were some circuits in there which you had a bubble and you had a edge. So it was a negative edge triggered circuit or negative edge triggered component. Here it's simply a positive edge. So absence of a bubble would simply mean positive. So edge trigger means here, whenever there's a transition that takes place going from 0 to 1 or 1 to 0, presence of a bubble means it's going to be negative edge, meaning a transition going from 1 to 0, falling edge. Otherwise, it refers to a rising edge. Rising edge. Okay, absence of a bubble is positive, so it means a rising edge. So what is the delay flip-flop? Well, a delay flip-flop is, again, kind of like a memory storage unit. It will store the memory, meaning the previous state. Hence, we see Qn minus 1, right? It will keep the output of the flip-flop in the previous state and will only change value or will only present the value from the input to the output when there is a transition going from 0 to 1. And only when the clock signal goes from 0 to 1 or transitions from 0 to 1, that is the only time when the output of a delay flip-flop will change value. And that changed value will depend on the value of D, which is the data input right here. So whatever value D is presented with, whether it's 0 or whether it's 1, will be sent to the output after a certain delay. That is when the clock goes from 0 to 1. When the clock goes from 0 to 1. That's what it means by delay. Yes. So the output is always on a delay. It only changes or only moves the input to the output. D is connected to Q. D is connected to Q only on a positive going edge of the clock. Okay, positive going edge. So if the level of the clock is at 0, doesn't matter what value D has, whether it's 0 or whether it's 1. Essentially, don't care. The output of D of the flip-flop Qn is always going to remain at the previous state. So Qn minus 1. Because that point D is not connected to Q. Yes.
So to trigger this, basically you want to trigger the D, give the value of D to change only in 1 to 0 or 0 to 1.
You tell me. Only transition going from 0 to 1. If there was a bubble, then it would work for 1 to 0, negative edge. But this is only a positive going edge.
So if we want to be more thorough with this chart, we could put a downward arrow for C and then X for D and then Q and minus 1 for Q and column.
You could, yes.
Okay, cool.
Yeah. So there was a transition taking place. So the point being made was, we add more lines to the truth table? The answer would be yes. If it's a falling edge, then it's nothing. It's just a previous state. Yes. Yeah, it's basically the system doesn't care what the input is. It could be 0 or it could be 1, but the output doesn't change. So let's explain again. Essentially, D flip-flop, what it does, it just connects the input D to the output Q. Okay, the input D is connected to the output Q after a certain delay, hence the name delay flip-flop. And the delay is provided by the clock signal. When the clock is activated, D is connected to Q. Okay, so when the clock is activated, D is connected to Q. So if D is 0, output Q is 0. If D is 1, output Qn is also 1. Okay, we good so far? Now the activation, for the activation, look at the symbol right here. The symbol is a positive edge trigger. Positive edge trigger means not just a value of 1, not just a value of 1. It has to be going from 0 to 1. 0 to 1. It has to have a transition going from 0 to 1. So if it transitions from 0 to 1, that's when the clock is activated. I mean, that's when the delay flip-flop is activated. And hence, the requirement is there should be a positive going transition. If it is a negative going transition, doesn't matter what the input is, output remains previous state. If clock is 0, again, doesn't matter what D is, it remains in a deactivated state, meaning the output stores the previous value of the output. The output stores the previous value of the output. So it doesn't matter what value D takes. If clock is 0, output is storing the previous value. So it acts like a storage bit. It's storing, the output doesn't change at all. So it acts like a storage, memory storage. If level stays at 1, output still doesn't change. Remember, it has to transition from 0 to 1. That's when it would change. So in the next slide, I have a timing diagram, and that would explain how it would work. So we have a D flip-flop. You're giving this as the clock input, and this is again referring to the previous diagram. So it is a positive edge trigger or a rising edge. Rising edge. Okay, so it's not sufficient only to have a level of 1. That causes confusion sometimes. If there are, In the previous class, if you recall, I was talking about how the level could be at 1 for a long period of time. And that could sometimes cause confusion in the operation of the circuits. So the output or the circuit becomes unpredictable. And so that's why we have a transition. We require circuits to respond to a transition, not just a particular level. Okay. So in a D flip-flop, if C, so here, if C goes high from 0 to 1, that's the only time when the output Qn will change, or not change, but at least, not at least, it connects the D input to the output. Okay. So let's look at where a positive transition is taking place. If I was to draw output Q, this is T time, and this is Qn. Where do you see a positive transition taking place in the clock? Right? It goes, so we don't know what was before 0. We assume it was going to be stay in that state, right? We don't know. If it was 0, then it would have stated, but it doesn't say that. So 4, 8, 12, and 16. These are the 4 places where you have a positive transition taking place, rising edge. So these are the 4 time periods, not time periods, but these are the 4 instances where the D flip-flop is going to connect the input to the output. Okay, input to the output. So we would assume that prior to 3, output was reset, meaning output was 0. If there is no indication, if nothing is given, then you can simply assume that it was reset, means output was 0. The positive going edge takes place at 4. What is the value of D at 4? So output is 1. Right? Whatever value D has, output takes the value, whatever the value D input has. That's it. That's what the flip-flop is doing. You're simply controlling when the data is transferred. Okay, so Q is equal to D, but that takes place only when the transition takes place. Make sense? All right. So it changes at 4. Then what happens after 4? It stays high, right? It's going to stay high. It stays high. Now, look at the truth table. The truth table tells us doesn't matter what happens, it remains in a previous state. It remains in the previous state. So it's going to remain high until the next time a positive transition takes place, which is at 8. At 8, what is the value of D? So then it goes to 0. Yes.
So from 4 to 6, E is in the positive trigger.
Where?
4 to 6.
So it stays at 1.
Right.
So 4 to 5, it stays at 1. 5 to 6, it stays at 1. But it doesn't, it's not, so it's not going to 0. It's not transitioning from 0 to 1. The only thing we care about is when it transitions from 0 to 1, when it goes in a positive direction. Nothing happens, just stays in a previous state. Just stays in the previous state. Yeah. So that's why Master made the point earlier. Can we add those 2 lines in the truth table, which is basically right here. So what happens if we have, a negative going transition? What would the flip-flop do? Essentially, it would just remain in the previous state. So Qn minus 1 acts like a memory. Doesn't change. Yes.
So basically, you are independently going.
Yes. D is the input. C is the clock. C is the clock. So here it would be don't care, and output stays at Qn minus 1. So it acts like a memory storage. It stores the information which does not get removed. And the next positive transition occurs at 12. So at 12, input D is 1, so output goes to 1. So at 12, output goes to 1. And then it stays at 1 until the next transition, which is 16. And at 16, D is 0. So output goes to 0. And then it stays there indefinitely. So in this case, in the timing diagram for a D flip-flop, or any kind of flip-flop, if there's an edge trigger, you want to see, first of all, where the transition is taking place. If there was a bubble, in the clock input, it would be a falling edge, meaning negative. So then you identify all the falling edges in the clock. And those are the points in time where the output would change, or output would equal D. Okay, so wherever you have a bubble, meaning the knot, it is responding to the negative transition. So negative transitions take place at 2, 6, 10, and 14. 2, 6, 10, and 14. And so every one of those inputs, it would see what D has, what value D has, and then it would simply replicate it at the output. So it acts as memory. It's storing the information till first and then you. D is the input. Yeah, and it's only a single bit input, so it can only take on 2 states, either 0 or 1. Yes, please. Yeah, rising edges, nothing would change. It would just stay, yeah. So the circuit would only respond to a falling edge. In case of a negative trigger, it would only respond for a falling edge. For a rising edge, it would not respond. It will just stay in that state. And that removes confusion, because a edge we can describe as an instant, like a really small moment in time. For a level, that level could last for a few milliseconds or a few seconds, depending on the time period. But an edge is an abrupt transition. And so that removes or avoids uncertainty in the operation of your circuit. Hence, we use edge triggers. So far we looked at the clock inputs where we were talking about levels. So in the truth table, it says right here, right? If the clock is at 1, it doesn't matter. It is not a transition. It's just a level of 1. So it doesn't matter what level the clock has, whether it's a flat 0 or a flat 1, the output of the flip-flop is not going to change. It is only going to respond for an edge, and hence an edge-triggered flip-flop. In this case, edge-triggered D flip-flop. Yes?
I know that we don't talk about devices, but do edge trigger devices make them
There is, yeah.
Okay.
Yeah. So, any other questions? Yeah. Do you have a question? Okay. Attendance is good, actually. Morning classes, I was walking down the hallway. There were like 10, 12 students in each classes. My morning class had like a total of like 15 or 16 students. So, no, one section. Some online, some in class. But one class in the morning had like 4 or 5. Yeah, so because of the uncertainty in the state of a SR flip-flop, when both inputs are 1, they added a few more components and created a JK flip-flop. A JK flip-flop, so from this point on, again, you're not looking at individual components or individual gates. Okay, we're simply looking at the flip-flop as a box. We don't care what is inside the box and how it's made. We only care about the input and the output. Okay. First thing, what do you notice?
falling edge trigger.
It's a falling edge trigger. It's a falling edge trigger. So the truth table has these falling edges right here. Falling edges. Right. So for rising edge, again, there's an absence, but for rising edge, the flip-flop is not going to respond. That would be the most important thing. The flip-flop won't respond for a rising edge. It only responds for a negative edge, hence the bubble. So if the clock is 0, if the clock is 1, flip-flop does not respond, output stays in the previous state. And I was stating we use it as a memory. It stores memory, right? It stores memory. It stores the data, hence we can say it's can function as a memory storage unit, 1-bit storage. Now, it only works when a transition from 0 to 1 occurs. Okay, so this JK flip-flop is exactly like SR. It works exactly like SR flip-flops, the set reset flip-flop. Okay, so the truth table is exactly the same. We've established that will only work when there's a negative edge of the clock. The first three states are basically the same as the SR flip-flop. Okay, you apply J is 0 and K is 1, your output is reset. You apply J as 1 and K as 0, your output is set to 1. In an SR flip-flop, it's exactly the same. S is equal to 0, output 0, S is equal to 1, output is 1. The uncertainty was when both S and R are both equal to 1 at the same time. And there, the output of the circuit could not be predicted. Depending on which input received that 0 or 1 faster, the output could be either 0 or output could be 1. So output was unpredictable, and hence designers state that this state is not allowed. Okay, as a designer, you're not allowed to have both inputs high at the same time. In a JK flip-flop, we remove this uncertainty and design it in such a way that when both inputs are 1, the output goes to the naught of the previous state. So Q n minus 1 naught, meaning the output is now toggling. If your output was previously 0, now it becomes 1. And if it was 1, now it becomes 0. And so it becomes what is known as a T flip-flop, toggle flip-flop. As a separate slide, I don't have that, but that's what a T flip-flop does. Basically toggles the output. So first, establish the fact that this is a negative edge triggered flip-flop, meaning it'll only function or it'll only change the state or only react when there is a negative going transition, meaning when it goes from 0 to 1. Right? That's the first thing. Meaning if the clock has a level of 0 or it has a level of 1, the flip-flop is not going to respond. It's going to stay at the previous state. Then next is we write out the 4 states for the negative going transition. And out of those 4, the truth table is exactly the same as it's for an SR flip-flop. That's where the JK came from. The JK was a development of the SR flip-flop to remove the uncertainty when both inputs are 1 and 1. Okay. For all other inputs, for these 3 states, it behaves exactly like the SR flip-flop. For inputs 1 and 1, it simply toggles the output from the previous state. Yes. Yes, that's the only thing that would change. So the question being asked is, what would change if the bubble was not there? If the bubble was not there, these arrows would simply be indicating a rising edge. That's everything will remain the same. The operation of a JK flip-flop is exactly like a SR flip-flop. In fact, if there was no edge trigger, If there was no edge trigger, I would remove all of this and just have the last 4 states. It would just say whatever the clock input is, whenever the clock activates it. So activation, again, you have to keep in mind the clock signal is used or was developed to synchronize the operation of your entire circuitry all at once. There are so many other building blocks in a circuit that you have to synchronize everything. Otherwise, everything would be uncertain. You would not be able to predict when your output's going to work, when it's not going to work. So the clock signal is simply activating the circuit. Once the activation is done, that's when the circuit functions. So you have to treat the activation separately and the circuit separately. Yes.
So, like in the SR, we treat the case to set up the 2 and 4.
2 and 4. Oh, well, here. So are you saying, is this equal to S and R? Is that what you're saying?
Yeah.
Yeah, similar. Yeah, similar. Set, reset. So output gets set when J is equal to 1. Yes.
It's called the JK flip-flop, not the modified SR flip-flop.
No, I don't know. I think it's named after the inventor. Not really sure, but that's what they chose. Yeah. As with most things in life, technology is weird. So if you're,
Oh my God, it's working with that gas.
yeah, then they'll blame us. So if you'll remember HD, high definition, when it first came out, so we are going on a bit of a tangent. So high definition televisions, video signals, when it first came out, DVD had 480 lines of resolution. Okay, 480 lines of resolution. So HD signals improved that to 720 lines of resolution, and it came to be known as 720p. So that has to do with interlace and progressive. So 720p was equal to 1080i. And if you had 1080 lines of progressive, it was 1080p, hence the name 1080p. So they would call 720p as as HD. Unofficially, it was half HD, and 1080p was full HD. So if they ignored the full, they were trying to say it's half HD, but they don't want to say it's half because it's a negative term. Like, yeah, negative connotation. So they would just say HD. Well, it is HD, but it's, not in that sense. And the way it works is these are horizontal lines of resolution. So it's horizontal lines of resolution. So this is if I'm correct, this is a 1080p projector. Your screen, which is 1080p, it has 1080 lines. Okay, so you can see there's a screen door effect right here. If you can see, if you're far away enough, we don't see it. But if you get up close to your television screen, you see something like a screen door effect, meaning you can see the individual lines. So there are 1080 lines in the horizontal direction, and there are 1920 lines in the vertical direction. Hence it is, resolution is 1920 by 1080p. 1080. Then came, so what I was saying, then came the higher resolution. So they doubled both. They doubled the resolution. So here, this resolution became 1440p. And this one actually became 3860 because it's twice, right? It's twice. So twice the full HD resolution is what we call 4K. This is now known as 4K. In reality, this 4K should be 2160p. So no one knows why or how. So somebody decides to pick some terminology at first, and then it just sticks, and then it gets lost. Anyway, so this is just the recent confusion, and that's why it's, yeah. Anyway, let's get back to our lesson. We have just 2-3 more circuits to finish up. Shift registers, we take delay flip-flops. So why we talked about the delay is because they are the building block of memory. The memory storage that we use is known as a register because it registers the input and it stores it and then it forwards it upon depending on the circuit conditions. So in this circuit, you see 4 D flip-flops, and the output of each flip-flop is connected in series or sequential. Actually, cascading is a better word. Cascading connection. Meaning the output of the first one is given to the second one, input of the second one, output of the second one is given to the input of the third one, output of the third is given as input to the fourth one. Each individual output is also taken out, and so you have Q3 to Q0. The data is sent from the left, right? D0 is the least significant, remember, right? 0 is the least significant bit, and then 1, 2, 3. So in here 3 is the most significant bit. So the input comes in serially, output goes in parallel. So this is a serial in parallel out shift register. The data comes in one at a time, and it's stored, and when the clock arrives, it's all sent out in parallel. So this is a serial transmission. We also have, and so this is a reason why we need a clock, right? We need a clock to synchronize the operation of all 4. These are only 4 bits. Each word or a byte is 8 bits, right? Each byte is 8 bits. So there will be 8 of these just to handle like 1 word. And think about how many address lines we have. Yes. Digital word. Digital word. Like 1 digital word is known as a byte. And when we say in computers, when we talk about like we had like hundreds of bytes of data or 1 kilobyte of data. Each byte has 8 bits. So a byte is indicated. I think didn't I cover this in the first? I think yeah. Byte is indicated by a uppercase B, and a bit is indicated by a lowercase b. Okay. So the data that we use in terms of storage, like, I have a 1 terabyte hard drive. Well, 1 terabyte is an uppercase B, meaning it has 1 tera into 8 bits. Okay, 8 bits. Anyway, this is a serial in parallel out shift register. Everything is synchronized by this positive edge triggered clock, because there are millions of these literally. So serial in parallel out, every time there is a positive transition, the data moves forward. So the data, this is the actual data that is coming in serially. Okay, this is the actual data that's coming in. The data moves through each of these flip-flops in a cascading manner, right? Because the input of each is connected to the output of the previous one. So if you look at the timing diagram, this is when it changes for Q0. Every time there's a positive going edge, that is when it changes, right? These 4 times. Now, for the right there, and there. For Q1, Q2, and Q3, again, it's only responding to a positive edge transition, but it'll respond only and only when the positive edge transition is occurring. And the output Q0 is then mated to Q1. Okay, D1, sorry, D1. So Q0 is connected to D1. And so when the data in comes in, this is 1 here, it goes to 1. It stays at 1 because there is no positive transition. If this is, so first positive transition, second, third, and fourth. A second positive transition, Q0 goes to 0. Then a third positive transition, data is 1, so it stays 1. The fourth transition, again, stays at 1 because the data is 1. After that, there are no more transitions, so the data of Q0 stays at 1. And then Q1, Q2, and Q3, so on and so forth, will only change when the next clock pulse arrives. So Q1 is activated when positive edge going trigger 2 arrives. Before, in the first one, all flip-flops are activated, right? All flip-flops are activated. But the input is 0 when the transition arrives. Okay, so think about this. The input to Q1, Q2, and Q3 is 0. So even though there's a positive transition taking place, the output of Q1, Q2, and Q3 does not change because the inputs for all three of these is 0. Okay, so it does not change. You know what? Let me stop right here because you'll need to explain this a little bit more. I'll cover this on Monday and we'll wrap up this chapter. Quiz on Monday, yes, absolutely. So that's the other part of the announcement. Quiz on Monday, based on what we have learned in the last week, mostly sequential circuits, maybe a little bit of combinational logic, but I'll post, I'll send an email and make a post announcement. There's going to be one on sequential circuits, but you'll have pretty much the next 4 or 5 days, maybe even until next Friday to take care of everything. Well, that's a good point. No, I'll have the homework assignment, but I'll make the due date later. Yes, yeah. So, yeah. Yes.
Will you be posting a thing on Canvas about the content that we covered on the final?
Yes.
Okay, cool.
Yeah.
And then what about all the quizzes, the grader and the grading?
Yes.
Oh, the thing you're going to post the quizzes.
Yes. Yeah. Yes.
It's